Sea level rise is a hard to quantify, yet critical risk of climate change, says Michiel Schaefer of Climate Analytics and Wageningen University, lead author of the study. Due to the long time it takes for the world's ice and water masses to react to global warming, our emissions today determine sea levels for centuries to come. Limiting global warming could considerably reduce sea level rise. While the findings suggest that even at relatively low levels of global warming the world will have to face significant sea level rise, the study also demonstrates the benefits of reducing greenhouse gas emissions. Limiting global warming to below 1.5 degrees Celsius and subsequent temperature reductions could have sea level rise by 2300, compared to a 2-degree scenario. If temperatures are allowed to rise by 3 degrees, the expected sea level rise could range between 2 and 5 meters, with the best estimate being at 3.5 meters. The potential impacts are significant. As an example, for New York City it has been shown that 1 meter of sea level rise could raise the frequency of severe flooding from once per century to once every 3 years, says Stefan Rahmstorff of the Potsdam Institute for Climate Impact Research, co-author of the study. Also, low-lying deltaic countries like Bangladesh and many small island states are likely to be severely affected. Sea level rise rate defines the time for adaptation. The scientists further assessed the rate of sea level rise. The warmer the climate gets, the faster the sea level climbs. Coastal communities have less time to adapt as sea levels rise faster, Rahmstorff says. In our projections, a constant level of 2-degree warming will sustain rates of sea level rise twice as high as observed today, until well after 2300 as shown in Figure 7, adds Schaefer, but much deeper emission reductions seem able to achieve a strong slowdown, or even a stabilization of sea level over that time frame. Building on data from the past. Previous multi-century projections of sea level rise reviewed by the Intergovernmental Panel on Climate Change, IPCC, were limited to the rise caused by thermal expansion of the ocean water as it heats up, which the IPCC found could reach up to a meter by 2300. However, this estimate did not include the potentially larger effect of melting ice, and research exploring this effect has considerably advanced in the last few years. The new study is using a complementary approach, called semi-empirical, that is based on using the connection between observed temperature and sea level during past centuries in order to estimate sea level rise for scenarios of future global warming. Of course it remains open how far the close link between temperature and global sea level found for the past will carry on into the future, says Rahmstorff. Despite the uncertainty we still have about future sea level, from a risk perspective our approach provides at least plausible, and relevant, estimates. Flooded dock. Sea levels around the world can be expected to rise by several meters in coming centuries, if global warming carries on. Even if global warming is limited to 2 degrees Celsius, global mean sea level could continue to rise, reaching between 1.5 and 4 meters above present-day levels by the year 2300, with the best estimate being at 2.7 meters. Credit, copyright Knudrich, Fotolia. American Metrology Society, November 2005. Debate over climate change frequently conflates issues of science and politics. There's a push on climatologists to say something about extremes, because they are so important. But that can be very dangerous if we really don't know the answer, Hinson 2005. In this article we focus on a particular type of extreme event, the tropical cyclone. In the context of global warming, tropical cyclones are better known in the United States as hurricanes, i.e., tropical cyclones that form in the waters of the Atlantic and Eastern Pacific Oceans with maximum 1-minute average surface winds that exceeds 32 meters s1. We follow distinctions between event risk and outcome risk presented by Sarowitz et al. 2003. Event risk refers to the occurrence of a particular phenomenon, and in the context of hurricanes we focus on trends and projections of storm frequencies and intensities. Vulnerability refers to the inherent characteristics of a system that create the potential for harm, but are independent from event risk. In the context of the economic impacts of tropical cyclones, vulnerability has been characterized in terms of trends in population and wealth that set the stage for storms to cause damage. Outcome risk integrates considerations of vulnerability with event risk to characterize an event that causes losses. An example of outcome risk is the occurrence of a $100 billion hurricane in the United States. To calculate such a probability requires consideration of both vulnerability and event risk. This article discusses hurricanes and global warming from both of these perspectives. At the end of the 2004 Atlantic hurricane season, many scientists, reporters, and policymakers looked for simple answers to explain the extent of the devastation, which totaled more than $40 billion according to the National Hurricane Center. Some prominent scientists proposed that the intense 2004 hurricane season and its considerable impacts, particularly in Florida, could be linked to global warming resulting from the emissions of greenhouse gases into the atmosphere, for example, Harvard Medical School 2004, NCAR 2004. But the current state of climate science does not support so close a linkage, Chernberth 2005. Tropical cyclones can be thought of to a first approximation as a natural heat engine or Carnot cycle, Emanuel 1987. From this perspective, global warming can theoretically influence the maximum potential intensity of tropical cyclones through alterations of the surface energy flux and/or the upper-level cold exhaust, Emanuel 1987, Lighthill et al. 1994, Henderson-Sellers et al. 1998. But no theoretical basis yet exists for projecting changes in tropical cyclone frequency, though empirical studies do provide some guidance as to the necessary thermodynamical and dynamical ingredients for tropical cyclogenesis, Gray 1968, 1979. Since 1995 there has been an increase in the number of storms, and in particular the number of major hurricanes, categories 3, 4, and 5, in the Atlantic. But the changes of the past decade in these metrics are not so large as to clearly indicate that anything is going on other than the multi-decadal variability that has been well documented since at least 1900, Gray et al. 1997, Lancy et al. 1999, Goldenberg et al. 2001. Consequently, in the absence of large or unprecedented trends, any effect of greenhouse gases on the frequency of storms or major hurricanes is necessarily very difficult to detect in the context of this documented variability. Perspectives on hurricanes are no doubt shaped by recent history, with relatively few major hurricanes observed in the 1970s, 1980s, and early 1990s, compared with considerable activity during the 1940s, 1950s, and early 1960s. The period from 1944 to 1950 was particularly active for Florida. During that period 11 hurricanes hit the state, at least one per year, resulting in the equivalent of billions of dollars in damage in each of those years, Pelkey and Lancy 1998. Globally there has been no increase in tropical cyclone frequency over at least the past several decades, Webster et al. 2005, Lander and Gard 1998, Alsner and Coker 2000. In addition to a lack of theory for future changes in storm frequencies, the few global modeling results are contradictory, Henderson-Sellers et al. 1998, Houghton et al. 2001. Because historical and observational data on hurricanes and tropical cyclones are relatively robust, it is clear that storm frequency has not tracked recent tropical climate trends. Research on possible future changes in hurricane frequency due to global warming is ambiguous, with most studies suggesting that future changes will be regionally dependent, and showing a lack of consistency in projecting an increase or decrease in the total global number of storms, Henderson-Sellers et al. 1998, Royer et al. 1998, Sugi et al. 2002. These studies give such contradictory results as to suggest that the state of understanding of tropical cyclogenesis provides too poor a foundation to base any projections about the future. While there is always some degree of uncertainty about the future and model-based results are often fickle, the state of current understanding is such that we should expect hurricane frequencies in the future to have a great deal of year-to-year and decade-to-decade variation as has been observed over the past decades and longer. The issue of trends in tropical cyclone intensity is more complicated, simply because there are many possible metrics of intensity, for example, maximum potential intensity, average storm lifetime, maximum storm lifetime, average wind speed, maximum sustained wind speed, maximum wind gust, accumulated cyclone energy, power dissipation, and so on, and not all such metrics have been closely studied from the standpoint of historical trends, due to data limitations among other reasons. Statistical analysis of historical tropical cyclone intensity shows a robust relationship to the thermodynamic potential intensity, Emmanuel 2000, suggesting that increasing potential intensity should lead to an increase in the actual intensity of storms.